So today on March 18th, 2024, we are recording second conversation with Professor Mukunda. In the first conversation, we learned that it was in 1960s that he entered active physics and started doing his research and so on. So Professor Mukunda, let us use that as a starting point and ask you, when you entered the physics research, particularly when you went to Rochester and saw the world of physics in your own way, what were the important areas of physics that people were looking at, and how did you see the world of physics from your own point of view?
Well, my exposure to physics, as I explained yesterday, was over this 1 year spent at the training school of the Atomic Energy Establishment. That was you can say, a crash course introduction to physics. As I mentioned, there was almost 40 different subjects we were taught and examined over a 12-month period. And then, as I again said yesterday, I was given the freedom to pursue my own interests in reading. And I mentioned two famous books which I read at that time in the TIFR over a 1.5 year period. One was Dirac's Principles of Quantum Mechanics, the second was Hermann Weyl, Theory of Groups and Quantum Mechanics. I forgot to mention the third book I went through in great detail was a very new book at that time, The Theory of Photons and Electrons by Jauch and Rohrlich. It was the first very systematic presentation of quantum electrodynamics, but paying a lot of attention to matters of notation and so on. It very famous book at that time. So that was my third book. When I went to Rochester, the graduate level training, it was really a superb experience. Over the years, I have come to believe that there is a difference in character between training of students at a higher level, in physics certainly, in Europe, the continental approach, compared to the US approach. The main difference is in the continent, as far as I am aware, UK and France and Italy, the students generally are expected to learn what they need to learn more or less on their own. The idea of a very well-structured coursework, training, well-defined courses one after the other over a 2-year period, that is characteristic of the US graduate school teaching in physics, and I imagine also in other science subjects. So that was a great benefit for me. One thing I did miss in Rochester, they did not have regular courses in general theory of relativity. They had courses in quantum field theory, renormalization, particle physics, apart from quantum mechanics, electrodynamics and so on. So that is something that I missed, and whatever I could learn about general relativity, I had to learn on my own. I suppose that was so in most universities at that time. There were a few places where general relativity was taught very, very seriously. Princeton University was one of them, University of Maryland, so on. But it was not true of every place. So because of my association, well, being in Rochester, there were two major possible areas I could have gone into. One was elementary particle physics, which is what I finally chose. The other could have been nuclear theory, because of the presence of Professor James French, a very fine physicist. And the third actually was modern optics. Professor Wolf had just joined Rochester a year or 2 years before I went there as a student. He brought all the modern developments of classical optics, that is his own creation, coherence theory, partial coherence, all that he had done in England while writing the Born and Wolf book, Principles of Optics. Soon after that was done, that was in the mid-50s or so, and that contained all his own work, he moved to Rochester. So that was a possible area I could have thought of, but as I said yesterday, I chose to work in particle physics. My colleague and contemporary Chandralal Mehta, he took up optics and he went to work with Wolf. Very soon after that, as you know, the laser had just been invented and the field of quantum optics just burst upon the scene, because people realized, see, in principle, quantum electrodynamics was invented by Dirac in 1927. That was the first step. And then Heisenberg and Pauli. And then throughout the 1930s, there were problems with the theory, the problem of infinities. Then the Second World War came. At the end of the Second World War, around 1947, 48, 49, the theory of renormalization was developed. And then quantum electrodynamics became an acceptable theory with ways to calculate physical effects quantitatively, which agreed with experiment. A way was found by Tomonaga, Schwinger and Feynman to hide or put under the carpet infinities in the calculation. Then what happened is that the weak interactions, they became very important. That was another long story. What I want to mention here is that after the birth of quantum electrodynamics, field theory came into its own. Quantum field theory came into its own. And over the years 1960s, 70s, 80s, 90s, there was a whole rebirth of quantum field theory. And so if you look at young people who are trained in these areas these days, it is such a great theoretical achievement. Of course, I missed it because it happened after my graduate student days. Also, my interest went in the direction of group theoretical ideas, algebraic ideas. So that is how I chose my field.
Mm-hmm. But that's from a personal angle. But then, like at that time, what were the big things happening in physics which you heard of, and what were the milestones which you saw at that time being crossed?
Well, the most important thing in particle physics certainly was the discovery of this higher symmetry, internal symmetry, SU3 by Gell-Mann. Curiously, it turns out that he first presented his ideas at a summer school in Bangalore, 1961. That was the first time he gave a well-organized set of lectures on the subject anywhere in the world. And so in that, but I had just left India. My colleagues Divakaran, Rajashekharan, they attended that summer school. So Gell-Mann was there, Dalitz was there, Bhabha was there asking questions all the time. So when I reached Rochester, in particle physics, these machines had come into operation, accelerators, and lots of, plus also cosmic ray physics, lots of new particles were being discovered. So the excitement in elementary particle physics was the profusion of unexpected new particles, semi-stable, things which live for about 10 to the minus 8 seconds or so, which is very long by strong interaction standards, but it is like beta decay or something. It's weakly decaying particles. So trying to find patterns of symmetry in which to arrange these particles was a very major effort. Sudarshan himself was working along those directions. The number of so-called distinct elementary particles was at one point about 200. Remember that 15 years before that, what are the elementary particles known in nature? Proton, neutron, electron and positron. After a while, the mu meson was discovered. Then in the 40s, the pi meson was discovered, and then the resonances. So that was a very major part of elementary particle physics, what was going on at that time. The results coming from accelerators, and that drove the search for higher symmetries. So that was one thing. General relativity was still not as prominent experimentally as it is today. This was, I am talking 60 years ago. So the work in general relativity, as far as I know, was more on the theoretical side. But the understanding of black holes was just beginning. And another colleague of mine who is no more, Professor Vishweshwara, who used to work in the Raman Research Institute, his very well-known work on properties of black holes was done in that period, 1960s. So these are some of the things. Apart from that, you know, the development of the laser, as I said, what I was saying about quantum electrodynamics was actually the following. In principle, quantum electrodynamics showed how to use the principles of quantum mechanics for the electromagnetic field, and renormalization showed how it could be made into a workable theory, avoiding all infinities. So in principle, all the properties of lasers, which is a particular kind of source of electromagnetic radiation, in principle that is all contained within quantum electrodynamics, but that is only in principle, not in practice. So what was important was to construct a theoretical framework for the quantized radiation states, which would be directly useful for processes involving initiated by lasers. And that is what happened. You can say in the mid-50s, Emil Wolf had created the classical theory of partial coherence. Soon after the laser was invented in 1960, by 62, 63, Glauber showed how to start constructing the form of quantum electrodynamics, the theoretical framework in principle known, but in a form directly applicable to the new experimental possibilities. So coherence, partial coherence, things of that kind. That is when Sudarshan discovered his diagonal representation. That is another direction which I could have entered, but that was also, because it was Rochester, it was very much in the air. We knew about it.
Of course, in that same following decades, so many other developments happened. So how did you kind of see them and perceive them, like the grand unified theories and electro-weak coupling and all that? So these must have made a big news in the world of physics? Or
actually, Sudarshan's own PhD work was on the V minus A theory of weak interactions, but that was a variation, a development of the Fermi theory of 1934, what is called the 4 Fermi interaction. And it was known from the very early days, it is not renormalizable. When Sudarshan and Marshak found that Fermi's theory has to be modified to include more terms, to take account of parity violation, it remained a non-renormalizable theory. So it was known that it's a very important step, but it cannot be the final word. The actual, now accepted completion of weak interactions, combining it with electromagnetism in such a way that it is renormalizable, that first steps were taken by Weinberg, Salam and Glashow. That was in the 1967-68 period. By that time I was coming back to India. I did not get to work in that field. But that was, and things like after their predictions, the W meson and the Z meson, those things were experimentally discovered in CERN. Then the impetus came to go for unifying not only weak and electromagnetic interactions, but also strong interactions. So that was grand unification, but that was some years later, 80s, 70s, 80s.
so you wrote this very well-known book on classical mechanics with Sudarshan.
Yeah.
So how did that project develop? Because your earlier research was not directly in that area.
True. As I mentioned, Sudarshan had given a course on classical mechanics to graduate students at Rochester in 1961, if I remember, from a very fresh perspective. He brought in elements of Lie group structure, Lie algebra structure, and showed how closely it is related to the principles of Hamiltonian dynamics. All right? And It was partly inspired by knowing the structure of quantum mechanics and then trying to do analogous things at the classical level. I also feel that he must have been inspired by Schwinger's approach to the whole subject. So, in the summer of 61 or 62, I can't remember now, maybe 62, my summer job was to write out his classical mechanics course notes in a coherent way, which I did, and it was like a preprint of those days, 150 pages long. Then soon after that, 2-3 years after that, we received a proposal from Wiley publishers. Would Sudarshan and I agree to write a book on the subject, and we signed a contract with them. But if I can expand a little bit on that, how that book came to be written, throughout my stay in the USA till I came back to TIFR in 1967, I could not find the time to work on the book. It was clear that I would have to do most of the writing, and Sudarshan would keep checking on it and contributing certain parts of it. So, it was somewhat amusing. Whenever we met once in a while, he would ask me, any progress with the book, and I had to say rather embarrassed way, not yet, but I will start. In the meantime, I had started reading and trying to understand another great development of Dirac in classical mechanics, the theory of singular Lagrangian systems. This is something which he first presented in Vancouver in the Canadian Mathematical Congress 1949. Then it was published in the Canadian Journal of Mathematics 1950 or 51. And that Sudarshan was aware of that work because he had been very close to Dirac in TIFR in 1952-53. So, I spent a lot of effort trying to understand that Dirac theory. It took a lot of effort from me. Then when I was back in Bombay, I remember very well, in February 1970, I decided I will put aside all my other interests and work, start writing this book. And that is when I started, and if it's okay to mention it, I formally went to the director, Professor M.G.K. Menon, and said, I wish to devote myself for a substantial amount of time to this project. Is it all right by you? He encouraged me. So, from February 1970 up to about May, June 1972, I was writing the book every day, and it grew. In the meantime, what had happened is that in my 2 years at Princeton, there was a course given by Bargmann, a one-term course on the theory of Lie groups and Lie algebras from a physics point of view. And it was a wonderful course. I took notes very carefully. So, that had impressed me a very great deal. So, that experience of learning from Bargmann, which is how I came to know about his work, and the fact that Sudarshan had tried to bring in Lie group ideas into classical mechanics, all of this combined in my mind, and from January, as I said, January 70 up to June or so 72, this was my work. Day after day I would keep writing, and all the chapters came out. I remember even now, some days it's just on the lighter side, I would on the average be able to write 8 or 10 handwritten pages per day from morning till evening. Some days I would say, being over ambitious, let me write 2-3 more pages today. And then next morning I would come, the last few pages of the previous day I would not find it satisfactory, so I had to rewrite it. So, I realized by experience the ease with which you can write and the quality which you can maintain in your writing, you should not push it beyond a certain point each day. This is a lesson I learnt, So, writing has been a great pleasure for me from that experience and otherwise also, but that is why it took about 2.5 years to write manuscript, to write the book. And in those days, TIFR had one master Xerox machine for the whole institute. It was a machine purchased from Poland, if I remember. Not a Xerox of the US, but it was a Polish Xerox machine, photocopying machine. And it was a very cumbersome machine. Each page which had to be copied had to be kept on some glass plate, and then some other gadget with powder in it had to be shaken by hand, and one page at a time it would be done. But they gave me this facility. Whenever I finished a chapter, it was by ballpoint pen on Indian quality paper. Those people would make a copy for me for safety, and I would send it by airmail to Sudarshan. So
do you have the handwritten book?
Handwritten book, I think so, but I am not very sure. It is now more than 50 years. I don't remember. I may have it.
Okay. If it is there, we should maybe just scan it for posterity.
Yeah.
So when you moved to Bangalore, then one sees that you had European collaborations, you had work expanded into other areas and so on.
Yeah.
So how can you tell us about that and so on?
See, there had been a very nice link between the group in Rochester and some particular group in Naples in Italy. It was partly the personality of Sudarshan's teacher, Robert Marshak. In the early 50s and onwards, he encouraged talented physicists from different countries of the world to come to Rochester and be trained there, and then they would go back to their countries. Quite a few names whom you may have heard became physicists through this experience. The man who wrote the book Messiah on quantum mechanics, he was a student of Marshak. Tullio Reggi, the Italian, who discovered Reggi poles, which is very famous, he was a student of Marshak. Okubo, Sudarshan himself. So there were many from European countries, Asian countries, Japan, who came to Rochester and worked in this way. So why I mention this, let me just connect it to what I am saying. On the Italian side, apart from Reggi, there was a strong connection with the group of theoretical physics in Naples, and in particular Sudarshan had many contacts with them. So in 1967, on our return to India, we did visit that place, my family and I, and we had contacts with them. I had also met some of them in the year I spent at Syracuse. So that contact was there, and so when it was time for my first and only sabbatical in 1979-80, Naples was one of the places I went to on the way back, and that from 1980 onwards the contact became more structured. So in the years after that I was able to collaborate with them quite effectively.
And in the later part of 80s and much more in 90s, so you got into this whole area of geometric phases. And how did your interest in that subject develop? And
that is very interesting and for me very satisfying. It turned out that I did not know about geometric phases until I heard Sudarshan give a talk about it in college in Kottayam, in his home state of Kerala, where he himself had been a student. So at the Kottayam CMS college, they had arranged a 3-4 day seminar to celebrate Sudarshan's birthday or something. I had also gone, N. Kumar was there, and there he gave a talk about this geometric phase work of Berry. That was 1986, I think, about 86. Then what happened is that I heard about Pancharatnam's work. The fact that Ramaseshan and Rajaram Nityananda had brought out and brought to prominence very much earlier work of Pancharatnam and showed that it is closely related to Berry's phase or geometric phase as discovered by Berry in 1983-84. So that was also in my mind. And then suddenly I realized what I had learnt from Bargmann. Not in his course, but one of the things I had read, there are some classic papers by Bargmann in this field in bringing out the physical importance of Lie group theory and Lie group representations. One of those papers of Bargmann, written in 1964 when I was in Princeton, was a new proof he gave of Wigner's theorem of 1931, the so-called unitary anti-unitary theorem. These things I knew vaguely and sometimes in more detail, but they were sort of floating around in the mind. And then I realized around 1989, 1990, 2-3 years after hearing about geometric phase on Sudarshan and this Rajaram and Ramseshan episode, I saw a connection between the quantities Bargmann had introduced in 64 and the Berry work and the Pancharatnam work. So then in 1990, to satisfy my own curiosity, I tried to work out everything systematically from beginning to end, bringing in all these little pieces I knew about. In that process, I found that what we now call the kinematic approach to the geometric phase, where ultimately you don't need any of the principles of quantum mechanics. It is just the use of a complex Hilbert space. The geometric phase is already embedded there, but we, Simon and I, were able to bring out the relevance of Bargmann's work. That had not been noticed by anyone up to that time. So for that at least we are given some credit. So that is how the geometric phase idea came. Once we, and so I think we wrote a paper 100 pages in print in 2 parts in Annals of Physics around 93.
I remember in 1991 later part in the Math Science workshop, you gave a set of lectures describing these ideas, the kinematic approach to geometric phases. I think papers came maybe
they were submitted 92 or so,
and then they came little
93,
later. 93 they came.
They were rather long papers. Each part 1 and part 2 about 60 printed pages each. So we wanted to develop it very comprehensively. We were able to do it. Put in whatever knowledge we had about differential geometry, Lie group theory, Bargmann's contributions to the Bargmann invariant as we call it. All this put together in a nice story about the geometric phase. That was a very satisfying piece of work. That is how it came about.
Parallelly in those years you also moved into this invariant squeezing and symplectic ideas in optics. So what was the origin of moving in that direction?
That part was again through Simon and Sudarshan both being in the institute, and Simon had very good knowledge of classical optical physics, polarization phenomena in particular. And Sudarshan was a master of quantum optics through the diagonal representation, and he had a great interest in optical physics, optical physics I would say. So all these things were in our mind, and Simon in particular was very knowledgeable about very detailed discussions of particular beams of light in classical optics, the so-called Gaussian shell model beams.
You wrote papers, you and Simon have many papers, even Sudarshan is an author in some of them.
That is something, it had been done to a limited extent by the optics community, by people I would say like Wolf, though he may not himself have contributed, but people with that kind of background. Because we had this group theoretical strength and quantum mechanical understanding in general, all the tools we had assembled in other problems we were able to apply here, and that is how the work on optics by the three of us came into being. Along with all this, there was a very happy situation. There was a paper by two Frenchmen, a very famous paper, Bacri and Cadillac. They brought out the importance of the so-called symplectic group in 2 dimensions for optical problems, for classical optical problems, and that fascinated me. That was the entry point for me to understand better the so-called real symplectic groups.
That's where the paraxial beams and all those came in?
Paraxial beam came through the work of Bacri and Cadillac, and so we found a way to handle polarization, description of polarization in a new way, in a systematic way. Up to that time, in most classical optics papers, either they talked of polarization only or of space-time dependent beams only. To do the two in a consistent, mutually consistent way, we found a way to do it. In that same process, personally I got to know the real symplectic groups. I mention it for the following reason. All our experience in elementary particle physics had led us to learn more and more about the complex unitary groups of all various dimensions. Beyond them, all classical compact Lie groups. Those were what were important in elementary particle physics. Of course, I am leaving aside the Lorentz group.
Yeah, you worked on
Poincaré
representations
group.
of
Lorentz and Poincaré
yeah.
group. Those are connected to space-time. But within the family of Lie groups, most physicists at that time were not familiar with the real symplectic groups. The strange thing is, they are fundamental to understanding the structure of a Heisenberg commutation relations, which is the basis of quantum kinematics.
And also of classical phase space and statistical mechanics and so on.
So that somehow closed a gap in our understanding. So the real symplectic groups, largely unknown to most physicists, was at the heart of the properties of the commutation relations in quantum mechanics. They are the starting point of quantum mechanics, and so we were able to bridge that gap. In that process, we learnt about symplectic geometry, we learnt about this Williamson's theorem, and that gave us a way to understand properly what is the meaning of a squeezed state for a multidimensional system. Not one degree of freedom, but any number. When is it squeezed, when is it not squeezed, what kinds of transformations can cause a state to become squeezed. All of these things slowly got clarified, and the paper we wrote together along with Datta and Simon, that 1995 paper in Pramana, that has been a great pleasure to. I am very happy we all wrote it, and I think you have also told me quite a few physicists working in different parts of the world have, and within India mathematicians even, have told us they came to know about symplectic, real symplectic geometry and the Williamson theorem through our simple-minded review article. So that was a very.
So changing the track, the track of the conversation a little bit. See, many discussions with you and your talks also reveal that you have been also interested in foundations of quantum mechanics, the foundational issues. So how did you become aware of them, and how did your interest in that develop?
So the interest, I think, developed during this sabbatical year. Up to then, I would say I became familiar with Bell's work sometime. His work was done in 1964, but I was not very familiar with it, but I started reading about it in the middle to late 70s. There was a beautiful review article in the British journal Reports on Progress in Physics, Olive and Goddard, a beautiful review of the Bell hidden variable idea. So I slowly started learning about it, and I became interested in it around that time. The point is that we were all taught quantum mechanics in India and in Rochester even in a particular way. Boys, these are the rules of quantum mechanics. This is how you must apply it. But in retrospect, I never learnt quantum mechanics with a built-in feeling of skepticism or questioning. Now I see Sudarshan himself always had a questioning and attitude towards the way quantum mechanics is normally presented. And I also have acquired over the years a great deal of admiration and respect to two other people. One was David Bohm, who went on trying to modify quantum mechanics to find new ways of looking at it, and his younger associate Aharonov. Aharonov, I don't know him at all. I have read a few of his papers, but I am amazed how for such a long period he would go on questioning quantum mechanics, find new things in it which nobody else would have thought of. You are aware of it. So many things he has done. So I feel younger people today, when they learn quantum mechanics, please learn the technical aspects as thoroughly as you can. Be able to do all the calculations you need to, but retain a questioning and skeptical attitude. Don't take what the textbooks say as the final word. This is what I would say about quantum.
From a historical perspective, I mean, when you were as a graduate student at Rochester, did people talk about Einstein's EPR paper and or these things were not really very important for physicists?
No, I would imagine a quantum mechanics course given in Princeton University would have mentioned.
Okay.
I am imagining.
Oh, you are imagining, but not elsewhere.
But certainly not in Rochester. Maybe at Cornell, yes. I acknowledge that there are the top schools in the US, maybe 10 or a dozen or whatever, and the quality of the student teaching is very high in those places. Rochester is the next rung. One has to acknowledge that. Certainly in quantum mechanics, which I learnt in Rochester, it was very valuable, but it did not create this questioning attitude towards the fundamentals. It was a way to teach how are the calculations to be done. That is the point.
So what are your plans now? What kind of things you are concerned about, and what kind of questions you are thinking of looking at? And
well, this is rather late in life to start something new. At the moment, as you know, we have some of these writing projects. We want to, things which had been started decades ago, I'd like to bring them to conclusion so that it is something done, and hopefully more people will find it interesting. Then I don't know if time and energy permit, I would like to learn some of the things which have passed me by. See, this Sudarshan did so many different things. This what we heard about in your seminar 2 days ago, the theory of open quantum systems. That is probably beyond me at this stage. But some of the Aharonov kind of things, weak measurement, contextuality, these things I would like to understand more deeply. There's a very nice expression I picked up from Alan Aspect some years ago. He said the first quantum revolution came in 1927 onwards, and that was the wave-particle duality. And a lot of people had difficulty with it, including Einstein himself. He tried to disprove it many, many times, but he couldn't. Now nobody questions wave-particle duality. The second quantum revolution is the consequences of entanglement, which has starting with Bell's work. So, I find that a very beautiful way of showing the first phase of quantum mechanics is from 1925-27 up to Bell. There is then you can say a phase transition, and new concepts which are important in quantum mechanics, which had not received attention earlier in the first phase, they are now at the center of attention. So, if possible, I would like to understand them in a deeper way, and if possible, make a contribution.
Okay. So, couple of last things I want to ask before we close this conversation. So, over this whole period, which is a long period where you have been associated with physics, who were the physicists who kind of inspired you, historically or contemporaries?
Well, apart from the people with whom I directly worked, that is Sudarshan himself and younger people, I would say my greatest inspiration came from Dirac. That is number one. He had a style of writing which I very much admire, and he had a way of expressing himself which I have tried to copy in my own way. Then the writings of Hermann Weyl, they are, see, Dirac's writing I have always found quite direct, and what he wants to say with effort on your side, you can understand, though some of the things he said are very demanding. His whole theory of singular Lagrangian systems, it took me a very long time to say, yes, I now really understand what he did, and that was purely classical. Hermann Weyl, on the other hand, I found it's very inspiring, but not that easy to understand. And in my mind, I have the impression the way Weyl would present any topic was to sort of give you a view from a very great height, a view of the whole subject, whole problem, and then fill in the details. Not build up the understanding brick by brick, but give you some kind of overarching understanding and then build it up. That is that my understanding of his style of presentation, but he has been a great inspiration. Then two more people, Wigner. Wigner I had seen in Princeton, I had heard him in some of his lectures, and this whole one-term course from Bargmann. So, these have been for me the greatest inspirations. I can repeat: Dirac, Weyl, Wigner, Bargmann.
Two areas of physics kind of developed or maybe started in front of you. So, one is string theory, which I suppose was not there when you were working on things, but then it started, it developed and so on. Another is it was there, but then was not so prominent, applications of quantum field theory to condensed matter systems and whole lot of things like superconductivity, superfluidity, all that. So, how did you watch these developments and what was your way of looking at them?
See, this the application, see, as I said somewhat earlier, the whole development of quantum field theory after renormalization has been a fantastic achievement. Unfortunately, I have not been able to keep up with that. Renormalization theory in QED, that much I was familiar with. I had studied it in TIFR through that book of Jauch and Orlik, but much later and very significant developments in quantum field theory, I wish I had gone into them, studied them more deeply. Many of my colleagues did so, but I was more attracted to the algebraic and group symmetry related ideas. That is one thing. So, on the condensed matter theory side, my understanding of the subject is very weak. So, I just couldn't pursue that. Coming to string theory, it is the mathematical skills you need to understand and work with string theory, they are of a very high order, and I had no opportunity to do it. if I had a collaboration with another person and learnt it with another person, then it might have been easier. But just like I have not been able to do anything meaningful in general relativity or quantum field theory or string theory, all of these things have passed me by. But I think it's now a bit too late. Yeah.
I mean, you have already delineated, if you find time, what are the kind of things you will be focusing on. Well, thanks for giving time today, and I think we had a very interesting conversation. Hopefully we will continue tomorrow and look at some other aspects and talk about it. I mean, yesterday it was a personal trajectory that we talked about, and today I thought we should talk about the physics part of it, how you saw it coming. But maybe as a last question, I should ask if you want to say something to young physicists who are now choosing their careers in physics, how they should kind of, having heard you talk about the way you did physics and your forays into it, how should they kind of look at physics and then choose areas within that? What should be the deciding factors?
Well, that's quite a difficult question to answer. One thing is, see, my own training in physics was 60 years ago. The phenomena at the forefront of physics today are very different from what they were at that time. So, in the whole area of relativity and cosmology, so much of experiment has come in. So, that is a very rich field, and so those who are able to move into those subjects, they are very attractive subjects. The amount of experimental information, analysis of information, just think of the cosmic microwave background radiation. What a lot of physics people have got out of it, and there are specialists in that subject. That had not even been discovered when I was a student. It was just discovered in 1965. So, that is one subject. Condensed matter physics is what condensed matter. That's a very rich subject. Somehow I did not have the taste or the inkling to go in that direction. Equally well, I was never able to think of working in nuclear theory, for example, nuclear physics. Somehow they did not appear to me as subjects which I could usefully do. So, I think a student should have an open mind, not be influenced by prejudices. That is the main thing. Learn the technical aspects to the best of your ability, and then step back from the technical aspects, view the different major areas and choose based on your interest. Each person has a different taste in physics.
So, I think we will close today's discussion. So, thank you very much for giving time, and it has been really very interesting talking to you.
Thank you.
Thank you.